Hi everyone, welcome to your second lecture in mathematical methods. In the last lecture, we looked at average rate of change and we did a few examples, we made a definition, and then we found the final definition that we were looking for, in that the average rate of change between 2 points is the slope of the line connecting those 2 points. Okay, so hopefully you've had a look at that lecture, have not skipped it, and have done the practice questions now. So we are at a good point to start off with the brother instantaneous rate of change. Okay, now we as calculus people are more interested in this one rather than average rate of change. Why? Because when you think about things and want to judge how well you're doing in some aspect, you want to know how well you're doing at the moment, right? So for example, in finance, are you at the moment making profit or losing money? Or in life, is your value going up or going down at this very moment? Okay, so not over like the last period of time, it's just very moment, like at this moment, like right now. Okay, so that is what instantaneous rate of change is. Okay, it's the rate at which something is changing at this very moment in time, not over a period of time, like average change rate was. Now, for example, right, we had our function f of x equals x squared, right? And we were looking at the average rate of change from 2 to 10, okay? Now, if you look at it from an instantaneous rate of change point of view, you would only look at the rate of change at 2, not from 2 to 5, not 2 to 3, no, at 2 exactly, okay? Now, why are we more interested in it? I already explained to you, and another reason is that it's not as simple as average rate of change. Now, why is it not as simple? Well, because you cannot apply the same basic things that you learned before. Okay, we can try that. I will give you a demonstration as to why that will not work. Okay, so we have our function f of x is equal to x squared, and we want to find the instantaneous rate of change at x equals 2. Now, the one way of thinking about this, if we want to do it with our previous method, is to think that the start is 2 and the end is also 2. Okay, so we can say the start is 2, 4. The end is therefore also 2, 4. The function increases by 0. The x values are also increased by 0. Okay. Now, if you don't already see the problem, you see it now. So when we put that on top of each other to find the slope or the rate of change, we run into this problem that we end up dividing by 0. Okay. In the math world, you're not allowed to do that. You know, this absolutely destroys everything we know about it. So we cannot do this. And that is really the main problem with using the previous method. And this is why instantaneous rate of change is a bit tricky. Now, we do not have the method yet, as in our class. We have not found the method yet of finding instantaneous rate of change. Now, we will do that together, but since we do not have a surefire way of finding the exact instantaneous rate of change, we will avoid that problem, okay? We will instead try and approximate it, okay? Get as close as we can, and then if we learn something, good on us, okay? So what we can do is we can look at this graph here, and instead of doing 2 to 10, we are going to do different points this time, okay? We're going to start with 2 and 3, okay, 3, 9. And then we're going to find the average rate of change from 2 to 3, okay? And then we're going to do 2 to 2.5, then 2.1. And we're going to get closer and closer to 2. Now, if you think about what I'm doing here, if I show the average, this is the line connecting 2 and 3. And then if I draw another point here, 2.5, and whatever that is, that will be the line connecting those two. Okay, you see that as we get closer and closer to 2, two things are bound to happen. First of all, we would eventually, I'll draw this in a cleaner graph. So let me just redraw the graph. Okay, here's a function again. Okay, and then we have a point at 2. Now, what will happen as you get closer and closer to 2 is that your line will only go through one point, okay, on the function. So instead of going through 2 and 10, it will only go through 2, okay, because that's what we are looking for, only at one point. And then that point, this is what the line would look like, okay? It only touches the function at 2. Now that is called a tangent line, okay? A tangent is something that only touches at one point, okay? So that's one thing that's going to happen as we get closer and closer. The second thing is, like the average rate of change, the slope of this line is going to be our instantaneous rate of change. Okay, now that we have those two things clear, and we know that as we get closer and closer, we would get to the average rate of change. Okay, but see, here's the thing, right? We can't just keep getting closer and closer. Like, there's an infinite number of steps in between. We could go 2.01, 0.001, 0.001, and until we get old and can't even do any more maths. So instead, we're going to use this brilliant trick called the limit. Okay, so for that, we will first redefine our problem a little bit. Okay, so our problem is this: we are trying to find the slope. Okay, where our start, okay, our initial value is 2,4. Okay, and we have a final value which is something after 2. Okay, so let's say it's 2 plus h. Okay, h is some small number, and that value is where our finishing value. So if we finished at 3, h would be 1. If we finished at 2.1, h would be 0.1, right? And then obviously the corresponding function value is therefore 2 plus h, okay, because that's how functions work. Now, there's no particular reason of using h. We could have used any letter. It doesn't matter. It's completely arbitrary. But let's just go with that. And here is what we are doing. What we are doing is we get our initial function or final function value, and we subtract the starting function value, and we have this, and we subtract the starting value. Okay. Now you would see that the 2's here cancel out, and that is good. We are left with this. Okay. And now what we are doing is essentially we just make h smaller and smaller, right? Now, once we get to this point, we just make h smaller and smaller to get numbers that are closer to 2, right? So again, if you see that if we do make h 0 in that we start and end at 2, there's no difference, okay? The h becomes 0. At that point, again, this would be a 0, which again, we do not want, all right? That is why we cannot still put in 0. Now, here's what we are going to do. We are going to define a limit, okay? A limit. A limit is used whenever you are taking small steps to something, okay? In this case, we are taking small steps to making h 0, okay? We are making it closer and closer to 0, right? That's what we are doing. So when you take small steps, you use limits, okay? And you denote this like this, okay? So you say limit as h approaches 0, okay? Approaches gets closer and closer to 0, okay? And now if we write this like this, this is what this whole thing means, okay? This is what I'm trying to say. I'm trying to say that the limit as h approaches 0, okay? So we are doing with this function inside here is we have a value, in this case h, and we make it smaller and smaller and smaller till it reaches 0, okay? Not actually at 0, we're just making it close and close to 0. Kind of like an asymptote. You know how we say an asymptote, like if you have a horizontal asymptote, you know, if we have this asymptote and the function goes like this, you know, we say it approaches that value, but it never reaches it. It gets closer and closer, never reaches it. That's kind of what the limit is, okay? All right, great. Now that that's out of the way, we can now use some algebraic manipulation, and we will use a bit of a trick here, okay? Now, keep your hats ready because they're about to get blown off. So let's say f of 2 plus h is 2 plus h whole squared, okay? take 4 all over h, which is equal to the limit as h approaches 0. Now, every time you write this, you have to include the limit, okay? Otherwise, you will lose a mark in the test, okay, or exam. So we do not want to lose those 3 marks. Just include the limit every time after the equal sign, okay, not before. We can expand that, okay, obviously. Plus 4h plus h squared, take 4 and 4 cancel out all over h, okay? And then we are left with, this. We can factor out the h's from here. So we are left with this now, okay? Now, here's the magic. We can now cross out the h's, okay? We are doing the same division, except now we can do it because we are saying that h is not actually 0, remember? H is approaching 0, remember? It's not actually at 0. That's the best part. H is not 0. Like we said, it's approaching 0. It's not quite there yet, okay? Funnily enough, once we have this, okay, now this is what we are at, okay? Now, we're just going to say, well, now h being 0 isn't a problem, so let's just let h equal 0, and you know what we get? 4. So m, the slope of that tangent line, is 4. So the instantaneous rate of change is 4. So yeah, it is, that's what I'm saying. It sounds a bit like a trick. It sounds a bit wrong, I guess, because you kind of avoid the problem for a little bit, you know? You just go, okay, well, I'm just going to make it smaller and smaller, but not actually at 0. So when I have to deal with the problem, like it's no longer an issue. And once I solve the problem, I just bring it back in, bring the 0 back in, and now there's no issues. So, you know, it is a bit annoying, but I feel like once you wrap your head around it, it does feel very natural and a bit intuitive. But it takes a bit of practice. But I assure you, once you do practice these, there's always a question in the exam, maybe 1 or 2 questions, okay? And those, once you practice it, it's 3 marks, okay? 3 marks, very easy. And yeah, another thing I have to mention is that this whole process of finding the instantaneous rate of change is called the first principles method. Because it's the first thing we found, I guess, sort of. It's the first principles method. And this is what we use to find the instantaneous rate of change, or the slope of the tangent line at a point, okay? Now that will be all for this lecture, all right? Again, you would have some problems to practice on. So watch the worked examples videos and have a crack at those problems. And yeah, just good luck.